Hello. Yeah. Hello, good evening to all of you, and welcome to Unacademy. Welcome to the NCERT series of geography, where one by one we are covering the concepts of NCERT of geography, and that too, the book of Fundamentals of Physical Geography. Now, last week when we started this, at that point of time, we made a promise that this is going to be a continuous lecture series whereby the aim is to have the complete coverage of NCRT within a set time period, and that should be more than sufficient for your examination as well. Now, with the help of animations, diagrams, charts, and also the recap material, we are aiming to provide you with a perfect arsenal for your preparation. Now, one expectation from my side is also that whatever has been covered, I hope that we have been able to revise that as well. Now, as a part of that, this week onwards, what we will be continuing is that while we will also be discussing the some of the previous year questions which have been asked from the topic, we shall also be asking you certain multiple choice questions. Starting today, we will be starting with four multiple choice questions from easy to slightly tough. But then I want you to apply your mind and tell me what is the answer of it. And then we will move ahead into the theories associated with the origin of continents and the oceans. There are three different theories that we are going to be covering today. That is the convection current, the seafloor spread, as well as the plate tectonic theory. But before that, this is the chapter that we have been covering, the fourth chapter, that is distribution of oceans and currents. Now, before we initiate the discussion, what did we study in the last class? We studied about the theory of continental drift, where we understood Wagner's point of view and his understanding about how the planet's continents and oceans could have been created. There we observed that Wagner had proposed and postulated that there would have been in existence a Pangaea surrounded by a global ocean that he would name as Panthalassa. And this Pangaea and Panthalassa, they basically reframed themselves in order to form the present day continents and oceans. We also studied the contradictions and the reasons provided by the continental drift theory, and also the reason why continental drift theory was rejected. Now, we move ahead to the other theories, that is the convection current seafloor spread. But before that, let us have a couple of revision MCQs in order as well. Starting with the first question for you. Now, I want you to write the answer in the chat section if you know. Regarding the interior of the Earth, consider the following statements. The density of Earth increases with depth primarily due to increasing pressure. The core is composed mainly of silicates rich in iron and magnesium. The mantle exhibits both solid and plastic behavior depending upon the depth. Which of the statements given above is or are correct? This is a simple question associated with the interior structure of planet Earth. Okay. Now, here it is quite simple question for that matter. Now, first statement, the density of Earth increases with depth primarily due to increasing pressure. This is true. As you move greater into the depth, that is where the compressional force tends to increases. So materials are much more closer to each other. So the first statement is correct. Core is composed mainly of silicates rich in iron and magnesium. Now, core is not rich in silicates. All of you are focusing upon iron and magnesium. But the key point here is not iron and magnesium or iron and nickel. The key point here is silicates. So, core is not rich in silicates. Silicates had come to the surface of planet Earth at the time of stratification. We had studied about the case of the stratification and the phase of evolution of planet Earth. So this is what you actually had to look for, not the case of magnesium. Magnesium still in some quantity is present in the core. So this second statement is incorrect. Mantle exhibits both solid and plastic behavior depending upon depth. Now, this is correct. The mantle initially is solid, then it is plastic in the region of asthenosphere, and then again it is basically solid in the lower portion of mantle. So the correct answer in this case is going to be A, 1 and 3. Okay? Now, then take a look at the next question. Which of the following correctly explains the presence of heavier elements like iron in Earth's core? Take a look at the options. Can we say density is of Earth is also due to stratification? It is there. Correct. That is also at the time of formation of planet Earth. So here, gravitational differentiation during early molten stage, solar wind pressure forcing heavy elements inwards, volcanic activity concentrating metals in core, meteoritic bombardment depositing heavy elements at the depth. So in this case, basically, what is the reason why you have presence of heavier elements like iron in the core? Owing to the case of stratification. Stratification, arrangement in layers based upon the density. And that is where gravity will end up pulling the materials of higher density inwards, and materials of lower density will be restricted on the surface. So this is where the correct statement is again A. Now, consider the following statements regarding Earth's evolution. Early Earth was in a molten state due to radioactive decay and accretional heat. Degassing of Earth led to the introduction of gases in early atmosphere. Hydrosphere formed before the atmosphere. So, which of the statements given is or are correct? Let me know. So, the first statement here, early Earth was in a molten state due to radioactive decay and accretional heat. This is actually a correct statement. Here, why most of you would have thought this to be incorrect was because of the case of radioactive term, isn't it? Most of you would have thought that because radioactive is used, it would be incorrect. But it is not so. Okay, I'll tell you why. Because when you had isotopes of potassium can also produce radioactivity. Radioactivity is not always associated only with uranium, plutonium, thorium, etc. So even certain isotopes of iodine, etc., they can also end up having the radioactive nature associated, right? But let's assume I am confused about the first statement. I don't know whether the first statement is correct or not. Let's go ahead with that assumption. Degassing of Earth led to the introduction of gases in early atmosphere. This is correct. Introduction of newer gases happened during the phase of degasification. The third statement, hydrosphere formed before the atmosphere. Can that be correct? Hydrosphere got into creation only after the phase of torrential rainfall. Hydrosphere was not created before the torrential rainfall. But atmosphere was present even when planet Earth was a molten object. At that point of time also, you basically had the presence of primordial atmosphere or a primitive atmosphere consisting of hydrogen and helium. So that basically means the third statement will be incorrect. Now I know 3 is incorrect. So this statement is eliminated. I know 2 is correct. So there is only one option which satisfies that. That is basically A. The correct answer in this case would be A, 1 and 2 only. So, in case whenever you have a doubt, please go through all the options and then arrive at the answer. Then, coming on to the next question. Which of the following statements best explains the existence of liquid outer core? The simplest question out there. Even introduction of gases, Srinadi, has been talked about. It is not talked about for the first time, right? In the last question, had it been talked about that introduction or the gases for the first time was produced, right? Then it would have been different. I hope you understand the difference. So, which of the following statements best explains the existence of liquid outer core? Increase in the temperature exceeding the melting point of materials. Okay. Once more, if I take a look at the option 2 here, degassing of Earth led to the introduction of gases in early atmosphere. It is saying that early atmosphere was in existence and then introduction of newer gases took place. It is not saying formation of the first atmosphere, right? So that is where I hope you understand the actual answer, that is 1 and 2 only. Okay. So, like this, I hope you have been able to revise. We will be having this questions associated with the portions that we have covered in the live sessions also. My aim is that this session should be your only destination. After this, even if you don't get time to pick up the book, this should be more than sufficient for you. And geography is something which should be truly understood by you. Okay. Now, I saw one of the concerns which was there that, sir, please don't leave the uh, initiative midway. We will not be leaving this initiative midway, but we need your blessings. Okay. And those blessings in the form of a like, a simple like, a share with your friends, and subscribe. That's it. And we ensure and we assure you that this will be completed for the subject of geography and for the other subjects as well. Okay. Banu Prakash, we are still in the very initial stages of geography. What happens after that is something that we live tomorrow for. Now, we come to the theories which followed the case of the portion of continental drift theory. One of them was the convection current theory. So, today, as I told you, we will talk about the convection current theory, the seafloor spread theory, as well as the plate tectonic, the formation of Himalayas. Now, when we say convection current theory, this was provided by a kind of a genius that was Arthur Holmes. Now, Arthur Holmes initially, just like I provided you with a kind of a background for the portion of continental drift, let me also provide you with the background here. Arthur Holmes was an individual who was initially interested in the subject of physics. Under the tutelage of the great scientist Rutherford, you would have heard about Rutherford as well. Now, under that tutelage and under that guidance, he had continued his research for physics. It was in that journey that he basically came across the concept of carbon dating. In fact, Rutherford and Holmes, they are also credited with coming up with the idea of carbon dating, whereby, based upon the radioactive decay in the rocks, you are able to calculate the age of rocks, fossils, etc. Now, when Arthur Holmes started to study this, that is when he got interested in the fact that what if radioactive materials are present in the interior of planet Earth as well? Now, if radioactive materials are present in the interior of planet Earth, they would be generating a lot of heat. Now, what would happen as a consequence of that heat? That is where Arthur Holmes provided a series of theories, even a theory associated with the formation of mountains. Formation of mountains also is something that he associated with radioactivity. Arrangement of layers of planet Earth is also something that he associated with the radioactive heat. So, based upon that, he provided a theory that is known as the convection current theory. Now, before going into this theory, what this theory was, I will show you what it actually means. What is this convection current? Let's suppose I am a new individual, I am a layman, I don't know what is a convection current. So, what is a convection current? Convection current, in the simplest of the terms, is the transfer of heat from one region to another via the movement of materials. In this very basic kind of an animation, you would observe, and something that you would have associated with, let's suppose, when you are boiling water in a pan. There also you would have come across this, that let's suppose you take the water in a pan and you put it for boil. Now, it is not the case that immediately the water will start bubbling. Slowly and steadily, what will happen? Materials at the lower level, they will rise up, get heated up, rise up, and colder materials from the surrounding, they will sink and replace it. So, what is happening here? The heated portion at the bottom, heat is provided only at the bottom region, heat is not being provided at the top place. But then the top portion also gets heated. Why? Because the heated portion travels and transfers the heat. Meanwhile, the colder materials being heavy, they sink, they replace the risen portion. And this is a continued movement. So, when you say what is a convection current, it is a very simple thing. That is transfer of heat, transfer of heat via movement of particles. Okay, that is what a convection current is, right? Distribution, redistribution of heat, fair enough. Now, in case of planet Earth, how can it happen? So that is where he proposed something very unique and radical. He basically said that, look, there is concentrated sections of heat in the interior of planet Earth at the bottom portion of mantle, something which is also produced by radioactivity and other aspects of heat. Now, mantle, which is otherwise in a solid state, mantle is in a solid state. But let's suppose all the heat which is being provided here, okay, all the heat which is being provided here, it partially melts that portion of mantle, partially. So that liquid portion will be lighter, and that liquid portion will heat up the portion above it. That will heat up the portion above it. And like that, you will have the heat which is getting circulated, just like a convection current in your pan. This will also have a convection current. Colder materials will sink and will get resupplied, whereas the hotter materials, they will rise to the surface. It can also lead to volcanism, volcanic eruptions on the surface. It can also push the land away from each other. In a nutshell, if you are able to visualize this animation, that is the entirety of convection current theory for you. Okay? But we will have a very quick recap about what this theory actually meant. So, when we talk about the case of the convection current theory, what does the convection current theory tell us? Now, by the way, if you take a look at and if you refer various different books, they have varying dates for when the convection current theory was provided. Some of the estimates indicate that convection current theory was initially provided in the late 1990s. Some of them will tell you 1920s. But majority of them, they tell you that it is in the 1930s. Okay. So here, basically, you have radioactive elements. Whenever you hear the name of Arthur Holmes in geography, isostasy, mountain building, the spread of continents, oceans, whenever you hear the name of Arthur Holmes associated with radiative heat, always the case of the radioactive heat which is provided. So, radioactive heat that basically generates the convection current, that generates the convection current. And here, the hotter materials, they tend to rise up. Okay. Now, that can basically push through in the form of volcanic eruption, and that can even push through the land masses. Land masses can actually move with respect to that also. That was the convection current theory provided by Arthur Holmes. Okay, I hope that is clear. Now, after that, the 1930s was followed by an era of war. That is the 1940s. Now, in the 1940s, the world was very different. World War II had started. Now, during World War II was also an era of great scientific advancements, by the way. One of the areas where the scientific advancements knew no leaps and bounds was actually the case of weapon systems. Now, this is where, during World War II, the Germans and the Nazis came up with a new weapon system. That was the U boats, or the present day submarines. Now, these submarines would be moving underwater and would suddenly emerge and would carry out attacks on the ships carrying weapons, armaments, soldiers, passengers, everyone. So the Allied forces, that is, the British, the Americans, all of them were really concerned. That is when they started developing a technology, and that technology was your sonar tech. Okay, sonar technology. What was the sonar tech? Sonar technology was basically which would emit the waves just like a radar, right? So you basically had, let's suppose this was the ocean. So on the ships which were floating, there would be certain equipments which would be associated, and they would emit signals. Okay, these signals, sound waves, would basically bounce back and would be captured. Okay. If, let's suppose, any submarine or anything else would be in the path, the signal would be different and you could detect it. That is where the sonar tech was used. Now, the war was over eventually. The war was won in 1945. What to do with so many sonar tech, so many new equipments, and so many boats that the Allied forces had invented? That is when you had an American expeditioner, naval expeditioner, with the name of Harry Hess. Now, Harry Hess used this particular technology to study the oceans. He was a naval expeditioner. He liked the sea. He wanted to explore the oceans. Till that point of time, mankind was under the impression that oceans, they appear plain above, they should also be plain underneath. But Harry Hess, basically, when he started carrying out his experiments, he observed something very unique. And what was the uniqueness aspect of it? Based upon certain observations, he proposed a theory, and that theory was referred to as the seafloor spreading theory. Now, this theory was also not perfect. This theory also had some of the lacunae. I will show it to you, other than this animation also, with the help of another animation, that what the entire theory was about. But before that, what was the seafloor theory, spreading theory based upon? These were supported by a set of observations. Continental drift theory supported by series of evidences, seafloor spreading theory supported by a series of observations. What were those observations? First, at the bottom of the ocean, you had the presence of mid oceanic ridges, which were the sites of active volcanic eruptions. You had active volcanism, which would be observed in these areas, right? Lava would rise up under the ocean. Now, think about it. Even today, if you tell someone that, underneath the ocean there is volcanic eruption, they will be puzzled that volcanic eruption, because in their minds they would have constructed an image that there is a mountain, on top of it lava emerges on the land surface. But does it happen underneath the ocean? Many of the people are still not able to imagine. So imagine what the situation would have been in the 1950s. So Harry has observed that there would be underwater volcanic activity in a series of relief features, and that would be the region of these mid-oceanic ridges. And that is where he got an evidence with the help of the rocks also. Now, what he also observed was that in these regions of volcanic eruptions, that is the mid-oceanic ridges, if you move away from this region of volcanism, age of rocks get older. Means what? It basically means age of this rock is similar to age of this rock. But the age of here, this one, it is older, but it is similar to this one. So there is a similarity of the rocks on the opposite ends of that seafloor, of that mid-oceanic ridge, but the youngest rocks are closer to the volcanic site, oldest rocks are furthest away from the oceanic volcanic region, right? So rocks on either side of mid-oceanic ridges, they show similar, remarkable similarities. Then this is the map, a very unique map. This is a map which is presented by NOAA. Now, NOAA is one of the most reliable geographical analysis and oceanographic and climatological analysis that you will get in the world. NOAA, along with United States Geological Service. So you can rely on that. Now, this map is the case of the age of the oceanic floor. If you observe this map in slightly greater detail, you will observe. Now, refer to this scale as well. Kindly refer to this scale. It refers to the age in terms of millions of years. Now, where do you find the youngest rocks? Youngest rocks represented by reddish color. These are the regions where you find the youngest rocks, isn't it? These are the regions and the stretches where you find the youngest rocks. Right. All these are your mid oceanic ridges. As you move slightly further away, you will find older rock structures. The green color you observe, around 100 to 120 million years. Right? So that again means mid-oceanic ridge, newer rock formation. Far away from mid-oceanic ridge, very old rock formation. Observe this region, by the way. That is the region of Aegean Sea, right? Aegean Sea, Ionian Sea. Here, the rock age is almost 260 to 280 million years old. That means here, the oceanic floor is as old as the time of Pangaea and Panthalassa. That is how old the oceanic layer here is. But then, when Harry Hess was observing the ocean floor, he would observe that nowhere would he be able to find the oceanic rocks which are older than 200 million years. Nowhere. Whereas over the continents, you can find rocks which are more than 3 billion years old. For example, in regions of Australia, right? In the regions of Australia, you basically have some of the rocks which are more than 3.2 billion years old. In our country itself, in certain parts of Karnataka, in certain parts of Jharkhand, you have rocks which are more than 2.5 billion years old. But then in the ocean, why is it that the rocks are nowhere older than 200 million years? So he came upon the observation that oceanic rocks are always younger as compared to the continental rocks. Even the case of sediments of oceans at the base of the oceans. If oceans would have been, let's suppose, older, thereby sedimentation would have happened. Thick layer of sediments would have developed. But here also, sediments on ocean floor are very, very thin. right? So this is where, based on these observations, he also supported it with the observation of earthquakes. That in the regions of, for example, the areas of the mid-oceanic ridges, you have the shallow focus earthquakes, mild earthquakes which are experienced. But in the region, what would be referred to as oceanic trenches, the deepest portion of planet Earth are the oceanic trenches. For example, here you have the deepest trench of planet Earth, and that is your Mariana Trench. Mariana Trench. What is the depth of Mariana Trench? Let me know in the comment section. Now, in these areas, you have earthquakes as well. So, based upon all of this, he postulated a theory that was the seafloor spreading theory. What did the theory tell us? The theory said that basically newer crust, newer crust gets created where? Gets created at mid-oceanic ridges. By the way, annotations of the PDF is still a difficulty for any of you. Do let me know. Is annotation of the PDF still a difficulty for you? You can, in case it is, you can download it from my Telegram page. Okay. From tomorrow onwards, I will put it on my Telegram channel. You can download the annotations after the class itself. Okay. Don't worry. All right. Now, newer crust gets created at mid oceanic ridges. Now, hereby, it pushes the existing seafloor. As you can see in this animation, newer crust is getting created through volcanic eruption. And what is it doing? It is pushing the existing seafloor on the sides. Existing seafloor to the sides. Okay. And if it is basically pushing the existing seafloor to the sides, oldest crust gets consumed. Where? Gets consumed at the region of oceanic trenches. Oceanic trenches. This was his overall theory. In 3 points, you can actually summarize the entirety of the seafloor spreading theory. So, what is it? That basically you have the case of volcanic eruption at the region of mid oceanic ridges, which is pushing the seafloor to the sides, and the older seafloor gets consumed. So, in a way, if you think about it, what did this theory tell the world about the crust? This theory told the world that look, when it comes to oceanic crust continuously gets recycled, whereas continental crust is not disturbed. So, as a consequence, you will never have the situation where the oceanic crust is older than 200 million years, because continuously newer crust is getting created, older crust is getting destroyed, again newer crust is getting created somewhere, older crust is getting destroyed. You don't have such phenomena in the land areas. That is what Harry Hess had said. So, based upon this, Harry Hess basically postulated the seafloor spreading theory, right? He also evidenced it with the help of the earthquake seismic events, which would be concentrated around the areas of this mid oceanic ridge. The same mid oceanic ridge that we had shown the map of, most of the earthquakes would be concentrated in those areas, which indicated that newer crust or volcanic earthquakes are occurring in this region. This is basically how, as and when the newer crust is getting created, you would have the seafloor which would expand. As compared to earlier, the seafloor could expand. Now, remember one thing: when you had Alfred Wagner trying to explain why North America and South America moved away from Europe and Africa, respectively, what was Wagner's reason? Wagner had said that it was moving away because of tidal force or the force of gravitation. But Harry Hess basically said that no, the entire Atlantic Ocean was not present 200 million years ago. Atlantic Ocean, in fact, got created 200 million years ago when you had the seafloor spread. Okay. Now, what could be the mechanism of seafloor spreading? Convection current, which was earlier provided by none other than Arthur Holmes. Right? So, long after Alfred Wagner died, pieces started fitting into place. Right? But then, still, seafloor spreading had certain lacunae, had certain drawbacks. What were the drawbacks? It only talked about the oceanic region. It did not talk about why the land masses behaved in such a way. It told us that, okay, an existing sea can expand. But why is it the case that regions like India separated from Gondwana land? It did not talk about it. He only talked about in the case of the ocean floor, why volcanism occurs at mid-oceanic ridges. But he never talked about the fact that why oceanic floor has various other irregularities, underwater mountains, isolated plateaus. Why does an ocean floor have these kind of formations? So seafloor spreading theory also had limitations. Now, time passed by, but I will provide you a kind of a timeline. So, earliest you had the case of continental drift theory provided by Arthur Holmes. Arthur Holmes, when? 1912. No, Alfred Wagner. Just to check how many of us are awake. Now, then you had convection current theory, Arthur Holmes, provided in 1930s. Right? Then, seafloor spreading theory, provided by Harry Hess, and this was done in 1961. Now, what was the aspect or the chief outcome of continental drift theory? The chief output was continents can move, isn't it? Continents can move. What was the chief outcome of convection current theory? Heat from the interior travels to the outside. Movement within mantle, which can push the land away, can push the land away. Seafloor spreading theory. What did it talk about? The creation and the destruction of the crust. Creation of a newer crust and destruction of older crust. Isn't it? Creation of a newer crust and destruction of the older crust. All these theories had this kind of a provision that they managed to provide, or their contribution. Now, each one of them eventually led to the formulation of the theory that is acceptable today. That is the theory of plate tectonics. Okay. Now, you see, what happened in the 1960s? Now we come to the important theory from where the question is asked. By the way, this is those of you who are interested in answer writing, this is one of the favorite questions of UPSC, which it has asked in the optional as well. Okay, it has asked in the optional as well as in the GS. This is the favorite question, that is, explain how the earlier theories contributed to the plate tectonic theory. Okay, so you can try to write an answer of this as well, but after we have talked about the plate tectonic theory. So, what is the plate tectonic theory and what happened? So, you see, there was lot of study which was already done associated with the various different regions of planet Earth in terms of earthquakes, volcanoes, etc. Now, when people observe the regions of earthquakes, this is the case of the earthquake distribution across the planet. Now, you will observe that the earthquakes did not occur randomly anywhere and everywhere. If you actually observe, earthquakes, they do occur in a certain pattern around the region of Himalayas, around the region of southern Europe, around the region of the entirety of Pacific, isn't it? Earthquakes occur in greater concentration, right? Now, if you basically match it with the map indicating the volcanoes, it has a great similarity. This is the map indicating the volcanic eruption, major volcanic eruption in the past century, major volcanic eruption. Again, the same areas, the same regions, isn't it? So, based upon the study of this, people like you had Mackenzie, Morgan, right? Wilson, Tuzo Wilson was one of the great luminaries of geography at Princeton, right? So Tuzo Wilson is accredited with much of the research which was done for plate tectonics. It is, in fact, Tuzo Wilson who eventually helped formulate the entire idea of the supercontinent cycle, which we will talk about maybe at the end if time permits. Not given in NCRT, obviously. Now, all of these people, when they were studying, and they were studying individually in groups, etc., they came upon a conclusion that all these areas of earthquakes and volcanoes, they are concentrated in certain areas only because the surface might be very weak in those areas. The earth's crust could have been very weak in those areas. Based upon that conclusion, they came upon the idea that the entire world is divided, or the earth's surface is divided into sections. So they said that lithosphere. Now, what is lithosphere? Lithosphere is basically your crust plus solid upper mantle, isn't it? Crust plus solid upper mantle above the asthenosphere. So this lithosphere is broken into subparts, into parts. How do we know that it is broken? Based upon the study of earthquakes and volcanoes. We know the weak areas, we know the strong areas. So that is broken into parts, and these parts are known as plates. Okay? These individual parts, that is known as the plates. And based upon the distribution of earthquakes and volcanoes, one could arrive at the major plates, the minor plates. Now, in fact, what was Wagner suggesting? Wagner was suggesting that North America started moving away from Europe, South America started moving away from Africa. But here, they came upon an idea based upon the distribution of earthquakes and volcanoes that it is not only continent or not only ocean which moves. Plates basically combine, plates will have, in majority of the cases, plates will have both continental and oceanic crust. And oceanic crust. Okay, that is what the plates will have. Now, based upon the size, the plates were divided into types. You had the major plates and the minor plates. Which were the major plates? So, if you take a look at it, Eurasian plate was a major plate, right? Then African plate was a major plate based upon the size, whichever were large enough. Then North American plate was a major plate. South American plate was a major plate. Then Antarctic plate was a major plate. Pacific plate was also a major plate, right? And you had one plate that is Indo-Australian. So based upon that, you had the classification into seven major plates and multiple minor plates. Which are the minor plates? Caribbean plate, Nazca plate, Cocos plate, Yuan de Fuca plate, Filipino Sea plate, Arabian plate, Anatolian plate. Multiple small plates also exist, Scotia plate, and so on. Okay. So here, which were the major plates? You had seven of the major plates, right? So you had African, then Eurasian, Indo-Australian, Australian, then North American, South American, okay? Then you basically had Antarctic and Pacific. These were basically your seven major plates. All of these major plates, barring the Pacific, all of the other ones will have both continental and oceanic crust. Both will be present in all the plates, right? For example, the portion of Bay of Bengal, some portion of Indian Ocean is a part of the Indo-Australian plate, right? Now, there is only one that is specific, only one major plate which is completely made up of oceanic crust. Oceanic crust. And you have ultimate large number of minor plates. Cocos, Nazca, Caribbean, Anatolian, Arabian, so on and so forth. All of these were basically minor plates. Okay? Now, Wilson basically gave the name, again, beyond the NCRT, I'm just giving you some background information. Tuzo Wilson, who was of Japanese descent, American of Japanese descent, Tuzo Wilson used the term tectonique. Tectonique basically means what? Tectonique basically means building, act of building something. Okay. When you create something, very good. When you build something. So that is where the term tectonique actually would refer to. Now, this tectonique basically eventually was converted into tectonic. Okay. So, what it initially meant was that the plates which are coming together, moving away from each other, they are building something. But it later on translated into plate tectonic. That is how the term plate tectonic was arrived at. So, this is what actually meant that multiple plates, major and minor plates coming together, moving away from each other, that is what is creating the case of the aspect of uh, the various different mountains, landforms, etc. Okay. Akshay, it is not ascent, by the way, it is referred to as accent. And tectonic is not an accent. Tectonic is the pronunciation of this term. Please understand, it is not an accent that I am trying to imitate here. It is the term how it is pronounced. Okay. So when you write here the case of K along with T, it is tectonic. Okay. Not the normal case of tectonic. And get a straighter look into the spelling of accent and accent. It will be better. So, here, that is the case of the plate tectonic theory and how the aspect of plate tectonic theory was arrived at. Now, basically, Mackenzie, Morgan, Parker, all of them, they suggested that when you have these plates can move only in certain direction and only in certain ways. So when we talk about the movement of plates, movement of plates can be in three different types. What are the three types of movement that the plates can have? Plates can either move towards each other, plates can move away from each other, or plates can move parallel to each other, right? How does it look like? So, there can be the case of the plates moving away from each other, right? Why do the plates move? We will come to it. But plates moving away from each other. That is what is referred to as the divergence of plates, movement away from each other. Whenever the plate moves away from each other, at that point of time, there is creation of a newer crust. That is why construction of a newer crust. That is why this is also referred to as a constructive plate margin. Okay? Leads to construction or creation of a newer crust. Creates newer crust. Okay? Now, for example, when we talk about the case of, let's suppose, seafloor spreading or expansion of the Atlantic Ocean, that is the case of divergence of plate. North America is moving away from Eurasian plate. South American plate is moving away from African plate. So that is what is leading to the divergence of plate. Okay. So that is where the divergence of plates can always lead to the creation of a newer crust. In most of the cases, you will observe here. This is the map of the various different plates. Observe here, North America is moving in this direction. Eurasia is moving slightly in this direction. So, newer crust is getting created here, right? South America is moving in this direction, Africa slightly in this direction. That is why, across this entire region, volcanic eruptions occur, leading to the formation of the newer sea floor. This is the reason why Atlantic Ocean is going to expand with the passage of time. As years will pass by, Atlantic Ocean will get more and more larger. It was not always the case. And this is the reason why the region of Iceland, this is your area of Iceland. Iceland is going to expand in area because more eruptions will create newer crust and Iceland will continue to grow larger and larger in size. Okay. In fact, you had an incidence in the 1770s. In 1770s, what actually happened in the region of Iceland? You had a large crack, almost 37 kilometers in length, okay, which opened up across Iceland. And you had molten materials which started coming up and it spread over. Thousands of kilometer cube of molten lava spread over that region of Iceland. Right? Imagine wherever you are living, imagine somewhere 37 kilometers away from your home. Imagine if that large a crack opens up across the surface and molten materials start to come up. This is where you basically had the very famous Laki eruption. All of this is indicative of the expansion of the sea floor in the region of Atlantic. Now, yes, correct, Akshay. In this case, what scientists have recently found out is that the same thing has been happening here also, which has created the Red Sea. Otherwise, earlier, the Arabian Peninsula was actually attached to Africa. Not long time ago, Africa and Arabian Peninsula were together, but they split. Red Sea, etc., Gulf of Aden were created. Now you have a kind of a divergence or a split which is happening here. So Africa going into the future will be split into two parts. It is already begun. That is where you will find in this area you have Kilimanjaro, Mount Kilimanjaro, which is indicative of the split. You have Lake Victoria, Lake Tanganyika in this region, right? All the various lakes in this region. This region already has experienced a depression. The land has started to move away. And this is what is famously referred to as the African Rift Valley. African Rift Valley. So, this is what divergence of plates can lead to. Okay. Then, thereafter, the plates can move towards each other. When the plates they move towards each other, they will collide. Okay. But their behavior will be different. Yes, correct, Likit. When divergence occurs in continental crust, it creates a valley of sorts, that is the rift valley. That is what is also rifting. Okay. Rift means what? What is the meaning of rift? A divide created by tension, isn't it? Rift is something that you use even in your English language. You use the term that the rift between India and Pakistan keeps on increasing. That means what? The tensional divide between the two countries politically, uh, overall, the aspect of the society keeps on increasing. So that is what a rift basically means, divide created by tension. So, whenever you have materials pulling away, there will be a divide. In the land areas, that divide can create valleys and oceans, hence the African Rift Valley. Okay? Convergence. The plates are moving towards each other, crushing towards each other. Now, this can lead to convergence. One plate will get consumed in the region of the mantle. Volcanic eruptions, earthquakes, etc., become common. So that is why convergence of plate is also what is referred to as a destructive plate margin. Why? Because a portion of the crust is actually destroyed. Destructive plate margin. Now, depending upon whether it is a continental crust or an oceanic crust, convergence is going to be different depending upon whether it is continental or oceanic, right? So you can have three types of convergences based upon which crust is concerned. You can have continental continental convergence, continental oceanic convergence, or you can have oceanic oceanic convergence. Okay. Ideally, the lithospheric plate gets destroyed, but because the mantle gets recirculated, that is why the term, generic term used is crust, overall, referring to the lithosphere itself. It is the plate and the lithosphere which gets created and destroyed. Okay. Now, let us take a brief look at each of these different types. It is not mentioned in NCRT, but your study will be incomplete if you don't know about the details of it. So, types of convergences will be threefold: continental continental, oceanic oceanic, and continental oceanic. Starting first of all with the case of the continental oceanic convergence. Whenever you have continental oceanic, the heavier of the crust or the heavier of the lithospheric plate will undergo subduction. Okay, heavier plate will undergo subduction. Oceanic plate is always going to be heavier. Remember, we had discussed in the previous session that basically the oceanic crust oceanic crust is always heavier than continental crust, so it is always heavier. And as it is always heavier, undergoes subduction. Subduction. Right? Yes, the steel and the thermocol example. Now, as the oceanic plate undergoes subduction, observe something. Here, it will create deformation also. Slight deformation will be created, isn't it? So, what will actually happen will be somewhat like this: the continental crust will crumble under the pressure, right? This is your water. So here you will have the formation of an oceanic trench. Here you will have series of earthquakes which will occur in these areas as one oceanic plate tries to undergo subduction. But when the oceanic plate will undergo subduction, it will bring some silica in the sediments, some water. That water will evaporate, or not evaporate, but rather get converted into steam, because as you go into the interior of planet Earth, the temperature is increasing. This oceanic floor or oceanic crust is carrying that water underneath. The water gets converted into steam. Other materials melt, they rise up and form volcanoes. Okay. So on the sides of it, you basically have the formation of what? Fold mountains, volcanoes, and the entire zone is prone for earthquakes, seismic events. Okay. Now, yes, Harsh, but different kind of convergence. I'll show it to you with the help of animation, how the Himalayas got created. So basically, where do you experience this? You experience this in this area. That is in the region of South American plate and the Nazca plate. You experience this in this area, North American plate and the Pacific plate, as well as the Yuan de Fuca plate. You experience it in this area, part of North American plate and the Pacific plate. You experience it in this area, this region, right? In all these areas, you experience this. That is why this region is dominated by mountains, volcanoes, right? Andes being the longest mountain range in the world, volcanoes, Mount Aconcagua, Mount Cotopaxi, all of these are volcanic eruptions. Rockies have been created as a consequence of this. Volcanoes such as Mount Rainier, Mount Shasta, Mount Hood, Alaska Range. Aleutian Island chain has been created as a consequence of this. The Japanese volcanic region, for example, Mount Fuji, all of this has been created as a consequence of this. That is what is the reason why the entire region of Pacific has earthquakes and volcanoes, also known as the Pacific Ring of Fire. Okay, so this is the region where you have the oceanic continental convergence. You also have this to some extent in this area, southern Europe. That is why you have Mount Etna, Mount Stromboli, Vesuvius, all the volcanic eruptions which occur in this area of Sicily and the Italian peninsula. Then you have continental convergence. Now, in continental convergence, both the crust is light, no one is heavy, both are light. So, none of the crust actually undergoes subduction. Both of them collide, and that is where they start getting folded. So that is why continental convergence has always led to the formation of fold mountains. Example, you will have the case of Himalayas, then Alps in Europe, then Ural, the old collision which happened, right? All these are continental convergences. Okay. Then after that, you have oceanic. In the case of oceanic, which will sink, the heavier of the plate, whichever is heavier. So heavier oceanic plate sinks, right? Now, which is the heavier plate in the case of oceanic? Always older oceanic plate is going to be heavier. Why? Because older oceanic plate over a period of millions of years, more sedimentation, oxide formation, etc., would have happened, increasing the weight of it. Now, in the case of oceanic convergences, as one sinks, the other one gets deformed. And that is where, if this is your ocean, you have very deep trenches. Example, the Mariana Trench, and you also have volcanic eruption. These volcanic eruptions can grow to be so large, it can even create volcanic islands in certain areas, right? It can create volcanic islands. Example, the region of Indonesia and Philippines. All the island chain in this area of Indonesia, Philippines, the region of the Caribbean, the region around Japanese area, the Coral Islands, Aleutian Islands, they have been created because of convergence of oceanic crust with oceanic crust. In fact, even Andaman Nicobar Islands have been created because of this convergence. The oceanic floor of the Indian plate, when it collided with the oceanic floor of the Burmese plate, that is when Andaman Nicobar Islands got created. That is why India's only active volcano is present where? Barren Islands in the region of Andaman Nicobar group. Okay, last eruption happened last year itself. Now, so oceanic convergence, Pacific plate with the Philippine Sea plate, right? This is where you have oceanic convergence. Here also you have oceanic convergence. Wherever oceanic crust converges with the region of the oceanic crust. trenches get created. So you have the Mariana Trench getting created here. Then you have other type of movement where the plates neither move towards each other nor away from each other. They move parallel to each other. And that is what is referred to as the transform movement. Right? So neither when they will not move towards each other means there is no destruction of crust. When they don't move away from each other means what? No creation of a crust. Crust remains as it is. That is why this is also known as a conservative plate margin. Okay, plate margin. But this movement isn't going to be smooth, isn't it, guys? The movement isn't going to be smooth one. The movement will have lot of rough edges that the rocks will try to rub against each other. So oftentimes as the rocks try to rub against each other, there develops very large cracks. Any movement across these cracks can initiate earthquakes. The recent earthquake in Venezuela was a consequence of this kind of a movement. Earthquake in the region of California, earthquake in the region of Turkey, all of them are created because of these kind of faults, what are known as transform faults, because it is created due to transform movement of plates. Okay, so this is where you have the case of the plate movement. Now, one thing I want to take a look into is the region of Gujarat. If you observe the region of Gujarat, Gujarat is at the junction of three different plates: Eurasian plate, Indian plate, Arabian plate. Now, any movement across any of these areas will lead to disturbance of the region in Gujarat. That is why, other than the Himalayas and Andaman region, Gujarat is very prone to earthquakes. Bhuj earthquake as the famous example. And oftentimes, when these massive earthquakes occur, land oftentimes as a rebalancing, some land will go underwater, some land can be pushed up, etc. And that is the reason why on the coastline of Gujarat, you will find the submerged city of Dwarka as well. Evidences have been found in the region. Okay. Now, why do the plates move? The reason that the plates move is because of the interior heat of planet Earth. Interior heat of Earth. As simple as that. Substantial amount of heat is present in the interior, and that heat comes to the surface. It drives convection current, isn't it? Drives convection current. And this convection current basically ends up initiating the kind of plate movement. So you see, this convection current can push this landmass away from this landmass, right? Similarly, one landmass can be pushed here, here. So convection current generates divergence. But invariably, if you consider A, B, C, and D, B and C are being pushed away from each other, but C is thrown in the path of D. So here you will have convergence, right? Here you will have divergence, isn't it? Like that, you can have various movement. Yes, Pratibha, correct. Okay, so this is the mechanism why the plates will move, if at all, in one particular region. Okay, so a quick recap of the entirety of plate tectonic theory. Lithosphere is broken into plates. These plates move over the region of asthenosphere, driven by the internal heat of planet Earth, which generates the convection current. Now, then, very briefly, it has also talked about the case of the movement of the Indian plate. Even though the timeline is flawed, the timeline is not accurate, but nonetheless, how did the Indian plate behave? So, as I told you, Indian plate was not always present in the region of Asia. India was present in the region of southern hemisphere near the region of South Pole. Okay. Now, basically, if you observe this and listen to this carefully, in the late 1800s and early 1900s, the geologists, when they were basically trying to climb up the Everest and other portions of the Himalayas, they were surprised with the fact that in Himalayas you found rocks such as limestone. Now, limestone is a rock which can get created only under the oceans. In Himalayas, they found fossils of species such as ammonites. Now, you don't find ammonites on the land areas. You find ammonites only under ocean. But what were these marine evidences doing on top of the tallest mountain range across the world? Now, based upon that analysis, the scientists were able to recreate the movement of the Indian plate. And that is where they said that the region which now forms the Himalayas was at one point of time part of an ancient ocean. So, Indian plate, which was earlier the part of Gondwana land, it started moving northwards. As it started moving northwards, between the part of India and Eurasia lied an ancient ocean, which was known as Tethys. And that Tethys started to close up, it started to shrink, close up, sediments kept on getting deposited, and that region eventually got pushed up. That is how you had the entire formation of the region of Himalayas. So, what started was actually the northward movement of the Indian plate, right? So, initially you had Indian plate movement. Now, Indian plate movement, if you observe this animation very carefully. Now, I know we are taking the NCRT series, but this animation I have basically extracted from Caltech, right? California Institute of Technology, the case of tectonics. So please understand the details of it. Each portion is quite detailed here. So basically, Indian plate movement, if you observe this, it started roughly around 150 million years ago. So at that point of time, the speed of movement was very high, 15 to 20 centimeter per year. Now, as you can see, between India and Eurasia lied an ancient ocean, and that ocean was your Tethys Sea, isn't it? Now, as India was being pushed northwards, Tethys was also being pushed, right? So, this Tethys initially started undergoing subduction. So, at this point of time, Tethys was being pushed, right? So, can we say there was a convergence which happened between the Tethyan sea floor and the Eurasian plate, a kind of a oceanic continental convergence? Now, what happens in the case of oceanic continental convergence? Volcanic eruptions. So, on the side of the Eurasian floor, you had the volcanic eruption. Based on the evidence of the igneous rocks present to the northern part of Himalayas and the region of Eurasia, you get an idea that basically almost 5,000 square kilometer of Tethyan sea floor was pushed underneath Eurasian plate. Okay, so Tethys was pushed underneath Eurasia. Okay, almost 5,000 square kilometer. They basically underwent subduction. To the north of Trans-Himalayas, Trans-Himalayas were also created during the same folding process of the Himalayan region, right? Now, this is when you had this much amount of Tethys which was pushed, Indian plate then went ahead and created basically a kind of the entirety of the collision. So Indian plate, India and Eurasia collided. And when this India and Eurasia collided around 50 million years ago, observe the folding happened, land was pushed up, you had formation of Tibet. Okay. So, like that, you basically had the case of the entire formation of Himalayas, which happened simple understanding with the help of the animation. I hope it is easily understood if you observe and visualize this. Now, what I want you to observe in this, that how Madagascar in the very initial portion separated from the western part of India. So Madagascar was at one point of time associated with the western part of India. That is why still today, off the coast of Karnataka, of the region of Udupi district in Karnataka, you basically have an island that is St. Mary's Island. Observe that St. Mary's Island on the map. St. Mary's Island still has the kind of hexagonal volcanic rocks, which indicate a similarity of the rock structure in Madagascar. That is why St. Mary's Island off the coast of Karnataka is considered to be a geo-heritage site of India because it is an active evidence of the drift and the plate movement. Okay, so that is why it is these are the evidences which have helped scientists formulate that how this entire process has happened. Okay, so initially Tethyan sea floor and the region of the Eurasian plate, continent ocean, then you had continent, continent. That brings us basically to the end of the discussion. Today, we have discussed all the major theories, theory of the convection current, seafloor spread, as well as the plate tectonic. I hope that this session was helpful. This session has helped you visualize, with the help of animations in particular, that how the various formations have happened. Please do take a look into it, revise it. We have covered more than what is present in the NCRTs. If you have liked these animations and this method of interaction, let us know in the comment section. And don't forget us to bless us with the like, share, and your subscribe button. We meet again tomorrow. Till then, do take care of yourself. Goodbye. Thank you.